All right, my name is Riley Fecker, and this is my Physics 2 lab for circuits. So the purpose of this lab was to predict the behavior of circuits with resistors, use multimeters to measure the actual values of conventional current and potential differences in the circuits, examine behavior of ohmic resistors and capacitors. The model that we used was an RC circuit, which we created using the circuit construction kit with various uses of light bulbs, resistors, batteries, and capacitors. The physics concepts tested were energy conservation, steady state, loop rule, charge conservation, and Ohm's law. Results, brief preview, was that the potential difference around a closed circuit equals zero. Capacitor discharges slower than it charges. The negative reciprocal of the slope of the logarithmic graph of ln delta V over delta V initial versus time in seconds is the RC value of the circuit, and the system is the circuit, and the surroundings is everything around the circuit. This is just a brief look at those physics concepts we talked about earlier, with the left two being energy and charge conservation related to Kirchhoff's voltage law and Kirchhoff's current law, also known as node rule and loop rule. And then on the right, you see Ohm's law. So experiment 1, we had two 1.5 volt batteries, two resistors, one of them 47 ohms and one of them 10 ohms, or 100 ohms, and two ammeters. And the predicted current we found using I equals V over R, which is Ohm's law. So that I1 and I2 should be 0.02 amps, which is also the actual current of the circuit. The ammeter reads the same backwards if you flip it. And when connecting a voltmeter, it read 3 volts and the ammeter read 0 amps. This is because the total voltage from the batteries is 3 volts, but since it was still a closed, since we had to open up the circuit in order to attach the voltmeter, the circuit was not closed, so there was no current running. These are the potential differences across the different ammeters and resistors, and we found that if you add them all together, the potential difference around the circuit should sum to 0, and it does. And we set up the ammeter again, and the current still read 0.02 amps. This is the graph showing how the voltage changes across the circuit, and you can see that it starts and ends at 0. And the ammeter doesn't change when the voltmeter is attached because the voltmeter has very high resistance, and so it draws very little current from the circuit. These are the resistances calculated around the circuit. We found the voltage change across the area that we were trying to find the resistance of, and we divided that by the total current to get each of them. But V, BC, and VHG were both 0, and so the resistance on the wire and the resistance of the ammeter itself were 0 ohms because it was an ideal circuit in this case. Then we moved on to experiment 2. So when the light is connected to the circuit, the light shines brightly, and then it slowly fades until the current equals 0. When the capacitor is connected directly to the bulb, it discharges slower, and the current takes longer to slow. When the capacitor is charging and discharging, the current starts at max and goes to 0, and then using the 10 ohm bulb, the capacitor takes 5.5 seconds to charge and 7.33 seconds to discharge, and using the 20 ohm bulb, the capacitor takes 7.33 seconds to charge and 14.5 seconds to discharge. And this is the graph that we made, which we mentioned previously, which was the logarithmic graph of change in V over change in V initial versus time. And on the right, we can see the values that we took for time from 0 to 20 seconds and how that changed. And you could see that the RC value, which is resistance times capacitance of the circuit, was equal to 6. And then the actual resistor capacitance value we found by taking the negative reciprocal of the slope of this graph, which is 5.79, so that the results were fairly close to the predicted value. What if we were doing this lab in real life and we used an actual ammeter instead of an ideal simulated ammeter? Basically, real-life ammeters have some resistance and are not ideal, so there would be a decrease in current. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? So the ideal model showed the capacitor charging rather quickly, whereas in real life there would be increased resistance within the circuit, within the wire and such, and thus it would take longer to charge. And then the conclusion, the point of this lab was to demonstrate the relationship between capacitors and resistors in circuits, and the possible sources of error may have been human error, as I could have been off in time since I was typing by hand, but any other errors are very unlikely because the lab was performed on a computer simulation, so we're assuming ideal situations. Thank you.